Alright, happy Christmas Eve. Today we're going to be doing the second to last day of Advent of Code. Advent of Code, we've done two puzzles every day since the start of December, and today we're going to be doing the second to last one. So, very fun, very fun. Alright, so, day 24, lobby layout. Your raft makes it to the tropical island. It turns out that the small crab was an excellent navigator. You make your way to the resort. As you enter the lobby, you discover a small problem. The floor is being renovated. You can't even reach the check-in desk until they finish installing the new tile floor. The tiles are all hexagonal. They need to be arranged in a hex grid with a very specific color pattern. Not in the mood to wait, you offer to help figure out the pattern. The tiles are all white on one side and black on the other. They start with the white side facing up. The lobby is large enough to fit whatever pattern might need to appear there. A member of the renovation crew gives you a list of the tiles that need to be flipped over, your puzzle input. Each line in the list identifies a single tile that needs to be flipped by giving a series of steps starting from a reference tile in the very center of the room. Every line starts from the same reference tile. Because the tiles are hexagonal, every tile has 6 neighbors: east, southeast, southwest, west, northwest, and northeast. These directions are given in your list as E, SE, SW, W, NW, and NE. A tile is identified by a series of these directions with no delimiters. For example, ESENEE identifies the tile you land on if you start on the reference tile and then move east, southeast, northeast, and then east. Each time a tile is identified, it flips from white to black or from black to white. Tiles might need to be flipped more than once. For example, a line like ESEW flips a tile immediately adjacent to the reference tile, and a line like NWWSWEE flips the reference tile itself. So here's a larger example. Go through the renovation crew's list and determine which tiles they need to flip. After all the instructions have been followed, how many tiles are left with the black side up? Okay, so pretty simple. Today's basically about hexagonal grids. Shouldn't be too difficult, so I'll solve it and see you in a bit. Okay, so we have arrived at our answer. It is 276. I haven't actually tested this on the example. Okay, it's too low, so let's test this on the example and see if it works. Find out any bugs. Okay, so we just got our second answer, which is 332. Hopefully that is correct. Oh, it's too high. That's very strange. Okay, let's try again. Okay, so it turns out I was not implementing the flipping thing correctly. So I was not reflipping the coins, the tiles, as needed. But what? I need to wait 1 second? Okay, well, that's fine. That's fine. Boom. All right, let's go. Time to explain the problem. All right. Okay, so the idea here is that we have hexagons, and hexagons are great polygons. So we know that they're oriented like this because they have an east and they have a west, but they do not have a north or a south because there's no side that faces that way. If instead they were like this, then they would have a north and a south, but no east and west. But they're not oriented like that. They're oriented like this. They have a west and an east and a northeast and a northwest and so on. So we need to find a good way to be able to specify each, I guess, hexagon given a series of steps. So we need a coordinate system, and there's actually a coordinate system called axial coordinates. And there's this great article by, I don't know what their name is, but they go by Red Blob Games, and there's a great article on their blog about hexagonal grids. So I'll put a link to that down in the description. It's a great resource. Basically, axial coordinates are like this. So if we have a huge hexagonal grid like that, then there are essentially 2 axes, right? There's this axis that goes like this. So I'll draw it like this. Every hexagon in this line, so the hexagons are going to be really small, like that, and then that. Every hexagon in this line is going to have the same coordinate, and then every hexagon in this line is going to have the same coordinate. I should elaborate on this one. So we're going to call this the y-axis, and every coordinate here has the same y coordinate, I guess. So these are all y-axes. And then we have x-axes. X-axes go like this. They go in this direction. So every hexagon on these lines had the same coordinate. And we're imagining this as a big hexagonal grid, but it doesn't have to be the shape itself doesn't have to be a hexagon. It just has to be really big. I'm just drawing this for easier reference. So there are two coordinates, the x and the y coordinate. And this is really convenient because we can specify any hexagon using a y and an x coordinate. So if we have this hexagon, say over here, within this big grid, it has exactly one y coordinate and it has exactly one x coordinate. We can also do it the other way around. If we have a big hexagon, I know these are terrible hexagons. Okay. Okay. If we're given a y coordinate and an x coordinate, we can immediately know that there is one hexagon with that coordinate. So, how do we actually implement this? Well, it's pretty simple. If we are given our reference hexagon, for example, or any other hexagon where we have to make a step from, east, we're going to consider we have the same y coordinate. So we start at 0, 0, right? X coordinate of 0, y coordinate of 0. If we step one step to the right, we're going to increase our x coordinate by 1 because our original x axis was this, and now it's over here. So our new x coordinate is going to get increased by 1. The y coordinate is still the same, right? Because it's still in the same line over here. So y coordinate stays at 0. Okay, so that's for east. And we can see that in our code over here. East corresponds to a change in x of 1 and a change in y of 0. Similarly, for northeast, we're going to be increasing our x by 1 because we go from this line to this line. So it's going to have 1. Y coordinate is also increased by 1, so that's 1. Okay, we can do this for all the other coordinates as well. So here's the entire map. This is northeast, northwest, west, southwest, and southeast. So these are all the changes in coordinates if we make one step in any given direction to change in the x and y coordinates. And we specify them in this dictionary here. So given a direction, east, west, northeast, northwest, southeast, southwest, we get a change in x and a change in y. The first coordinate change in x, second coordinate change in y. So that's the idea behind our grid. I'll put a link to this article in the description. It's very helpful. Very, very nice. Okay, so now let's actually go over the code. So what we want to do is we want to be able to find the coordinates of any given hexagon given a series of steps. So the first part in executing this is actually to write a function to get the coordinates of a given hexagon given just this line, because each line specifies one hexagon, right? So each hexagon is specified by a line. And how do we actually process this line? Well, if there's no delimiters, right? Because if there's delimiters, it's pretty easy. But if there's no delimiters, no spaces or anything, it becomes a little bit more difficult. So the important thing to note is that there is a southeast, but there is no south. So if we see the next two characters are southeast, then we know it has to be a southeast, not a south and an east, because south doesn't even exist. So we go in chunks of 2 or 1. If the next two characters are a valid direction, then we know it has to be that. Right, if the next two characters are valid, we know have to go in that direction. Otherwise, if the next two characters are not valid, like en, this is not a valid string, so we know it must be just e. For example, that was independent, my first and second example. So how do we actually do this? Well, we keep track of an index, which is where we are in our current string. So for example, it starts at 0. Let's use this string for an example. We start at 0. We also have an x and a y just to keep track of where we are in our process. We return this at the end to return where we ended up. So we have an index and an x and a y. Index is just where we are in the string. So we loop while the index is still in range. Okay, so first, if the index is within range to count the next two characters. So if it's from here to the beginning, then and the next two characters are a valid direction. So for example, at the beginning, it is within range, so it's within the first length minus 1 characters. We look at the next two characters. That's se. Se is valid, so we add that to. So we set our direction to be equal to se. Otherwise, so for example, in the next step, I'm just skipping over some of this over here. In the next step, we see SE again. Okay, so we do that. Then we see NW. NW is valid, so we also do that. NE is also valid. NE. And then we see WS. WS is not a direction, so we know this must be west. So if otherwise, if the next two characters are not a valid direction, then we just add our current direction, our current character, just one character. That's our direction. So now we have our character, which specifies the direction. Might be multiple characters as well. We must add that to. We must find the direction that it specifies. So we have the string. Now we need to find the change in x and the change in y. So we have that called changes. We add the x coordinate and we increment. We add the y coordinate. So that's our new x and y given our current direction step. I don't know why that's there. Then we just return them at the very end. Very simple. There might be some off by one errors here if you want to check if the next two characters are within bounds. That's a little bit confusing. Maybe you might have to do some testing on that, but it shouldn't be too hard to figure out. So now we have this function that gives us the coordinates of a given hexagon, given the string of where to get there. So given a string, given a string, we have the coordinates. Okay, now we have this set called visited. I guess we'd call it black to specify that it is the tile is going to be black. They all start out as white, so we don't have anything in that set for now. So the first thing we do is we just loop through every line in the data because that tells us whether to flip a hexagon or not. We get the coordinates of that using our function. If that coordinate, if that tile was already flipped over to black, then we need to flip it again, so it's not black anymore. Otherwise, if it isn't black, then we need to flip it over so it becomes black. And at the end, we just have the set of all tiles that are black, and then we can return them, return the length of that set. So, yeah, that's basically it for part 1. All right, part 2. The tile floor in the lobby is meant to be a living art exhibit. Every day, the tiles are all flipped according to the following rules. Any black tile with 0 or more than 2 black tiles immediately adjacent to it is flipped to white, and any white tile with exactly 2 black tiles immediately adjacent to it is flipped to black. Here, tiles immediately adjacent mean the 6 tiles directly touching the tile in question. The rules are applied simultaneously to every tile. Put another way, it is first determined which tiles need to be flipped, and then they are all flipped at the same time. Okay, in the above example, the number of black tiles that are facing up after the given number of days has passed as follows. Okay. After executing this process a total of 100 times, there would be 2208 black tiles facing up. Okay. This doesn't seem too difficult. This doesn't seem too difficult at all. This is just more cellular autonoma. So let's just do it. Okay, so we got our answer. It is 3787. It is correct. Let's go. Okay, so let's explain the problem. Oh, okay, let's explain. So this is pretty similar to Conway's Game of Life, if you know about that. Similar to previous days where there were cellular autonoma. But basically, since we're dealing with an infinite grid here, and we don't want to really put any bounds on the size of the grid like we did with the hypercubes, we're just going to keep a set of which tiles are black because all other tiles have to be white. So we just keep this set. It's the same set. And we do the same operations as in part 1 because, we have to assume that. Otherwise, all the tiles are going to be white and nothing is going to happen. So we flip the initial tiles to be black, and then we define a few new functions. First is get neighbors given a coordinate. This returns the neighbors given a coordinate. So it just returns the 6 neighbors for every change in a coordinate in this, I don't know, what's it called? Directory map? Direction dictionary, I guess. Direction dictionary. We add that to change to the current coordinate to get a list of 6 neighbors. And the code here is pretty simple. We just loop through all the directions, and then for every direction we get the change in the coordinates, and then we find new coordinates by adding them together, and then we add the new coordinates to our result. Okay, next is count neighbors given a coordinate. And, okay, yes, so basically we just go through all the neighbors. This is where our get neighbors function comes in handy. It also comes in handy in other places, but we just do that for now. We get the neighbors of a given coordinate for every neighbor if it's in the black tile set, then we add our total by 1, and then we just return the total. So this counts how many tiles are black of a neighbor. I mean, how many neighbor tiles are black given the current tile. Okay, and then we have, this is the same one as before. Now we have our iteration function. Okay, this is very fun. So basically, this just represents one iteration. This represents an update for 1 day. So first we have our stack. This is going to be what we iterate through to do our depth first search. It's basically our handy-dandy recursion thing, except it's iterative instead of recursive. If you don't know about using like stacks for like BFS and DFS, then I suggest checking it out. So yeah, okay. And then we have our visited set. This is just to tell us if we visited a tile before. And then this is our new black tiles for the next day, because all of them are flipped simultaneously, right? So we need to keep track of a new copy of the tiles that are black. For every tile that is black, we add it to our stack because we have to consider changing it. And then we have to add its neighbors because all of the neighbors of the black tiles have the potential to change next time because they have a non-zero amount of black neighbors. So then we loop while the stack is non-empty. We get the coordinates of the tile that we need to consider. If it's already visited, then we don't need to visit it at all. If it's and then we add it to our set of visited tiles, and then we count how many tiles next to it are black. If the tile itself is flipped to black and its neighbor count is 0 or it's greater than 2. Wait, I should probably pull up the rules. So if the tile is black and it has 0 neighbors that are black or more than 2 neighbor tiles that are black, then we need to flip it over so it becomes white. Otherwise, if it's not black, then it must be white. So we and its neighbor count is 2, then it gets flipped to black. So that's what we do over here. After that, we just have our new set of the tiles, and then we just return that. Okay, so that's an iteration. This code is the same as before. We just have to flip the tiles initially. After that, we just iterate 100 times and update the set of tiles each time, and then we are good to go. After that, we just print out how many tiles are black, and then we are done. So, so that's basically it for part 2. And that's it for day 24. We are almost done with Advent of Code 2020. It's been fun. It's been a fun journey. I've learned a few new things, and yeah, it's been fun. But we still have one more tomorrow, which is when we're in the resort and doing stuff, I guess. So I'm going to push this to GitHub right now. You can check out the code. It's going to be linked in the description. So we have pushed it to GitHub. You can check out the code. As usual, the playlist is also going to be linked in the description. And if you have any feedback, as always, please leave it for me in the comments or DM me on Discord, whatever you feel comfortable with. It's gonna be great. Okay, so that's it for Advent of Code day 24. Hope today's explanation was helpful. Hexagonal grids are fun. I'm gonna put links to that in the description. And see you tomorrow on Christmas Day. Yeah, have a nice Christmas Eve.